This is section 4.2 on the mean value theorem and Rowe's theorem. Okay, so on page 287, the topic is the mean value theorem. First, we have something called Rowe's theorem. Here's Rowe's theorem. You're welcome to put this on your formula sheet. Let f be a function that satisfies the three hypotheses, these conditions. F is continuous on a closed interval, a to b, differentiable on an open interval, a, b, and f of a equals f of b. Most of the functions that we'll be dealing with in this section, these first two conditions are satisfied. F of a equals f of b, meaning your two endpoints have the same height. Then there's a number c in a, b such that f prime of c is 0. That basically means the derivative is equal to 0 somewhere between a and b. And here are some pictures. So you have a continuous and differentiable function, continuous on a closed interval, differentiable on an open interval. Okay, so from a to b, same height, same height, same height, same height. Okay, so somewhere between a and b, the derivative is 0. Here, it's constant. Everywhere the derivative is 0. Here, it looks like it's over here. Here, it looks like there's two such places. You're allowed to have two, but Rowe's theorem says there has to be at least one spot, like so. Okay. All right, so that is Rowe's theorem, R-O-L-L-E theorem. All right, so let's get started with Rowe's theorem, page 291, 1 to 17 odd. Here's number 1, 3, 5, 7, 9, 11, 13, 15, and 17. Okay. And so looking at number 1, let's go show you a graph. Verify that f satisfies the hypothesis of Rowe's theorem on the interval from 0 to 8. Okay, so from 0 to 8, it looks like it's continuous. It's differentiable, meaning I can take a slope of the tangent anywhere between 0 and 8. And f of a equals f of b, meaning f of 0 equals f of 8, same height. Rowe's theorem says somewhere between 0 and 8, the derivative is 0. And it looks like there's one over here and one over here. So estimate the values of c that satisfy the conclusion of Rowe's theorem. Okay, that means where is the derivative equal to 0? It looks like 1 and whatever that is, 2, 3, 4, 5. So I would say the values of c that they're looking for are 1 and 5. Okay. Question 5, verify the function satisfies the three hypotheses of Rowe's theorem in a given interval, then find all numbers c that satisfy the conclusion of Rowe's theorem. So f of x is equal to this thing on -1 to 3. Okay. Okay, so this is a polynomial. In fact, it's quadratic. And we know a quadratic is differentiable and continuous everywhere. Since it's differentiable and continuous everywhere, in particular, it's continuous on the closed interval from -1 to 3, and it's differentiable on the open interval from -1 to 3. And the function value at the two endpoints is the same, f of -1, plug it in, 2 plus 4 plus 5 is 11, -1 comma 11. Plug in 3, 18 minus 12 plus 5 is also 11. Right, so the three hypotheses of Rowe's theorem are satisfied. Continuity on a closed interval, differentiable on an open interval, and endpoints of the same height. Therefore, there's a c in the interval from -1 to 3, such that f prime of c is 0. Find the c. All right, so I take the derivative. 4x minus 4 is 0. That's x equals 1. So the c value is equal to 1. That's all there is to it. Okay, number 9. Number 9, that f of x equals 1 minus x to 2/3. So that f of -1 equals f of 1, but there is no number c in the interval from -1 to 1, such that f prime of c is 0. Why does this not contradict Rowe's theorem? Well, let's see. Plug in -1. -1 to the 2/3 means I square -1, which is 1. Take the cube root, I get 1, and 1 minus 1 is 0. Plug in 1, I also have 1 minus 1 is 0. So the two endpoints have the same height. However, the derivative is negative 2/3 x at negative 1/3, which is negative 2 over 3 x at 1/3. That cannot equal 0. Okay. That's not a contradiction of Rowe's theorem, because you will notice f is not differentiable everywhere between negative 1 and 1. In particular, the function is not differentiable at 0. Okay, so that does not violate Rowe's theorem, because Rowe's theorem says the function has to be differentiable everywhere between negative 1 and 1, and it's not differentiable clearly at 0. Okay, so that is Rowe's theorem, and now we will lead up to the mean value theorem, so the second part of this section, which is based on Rowe's theorem. Okay, so mean value theorem on page 288. Let f be a function that satisfies the following hypotheses. Okay, f is continuous on a closed interval a to b. That sounds like Rowe's theorem. Differentiable on the open interval a to b. Sounds like Rowe's theorem. But notice there is no condition 3. We don't have to have the two endpoints the same height. Then there's a number c in ab such that f prime of c is equal to f of b minus f of a divided by b minus a. Number 2 says the same thing, but this is the way you normally want to think of it. The idea is that, okay, these 2 points do not have the same height. There's a slope connecting them. The mean value theorem says somewhere between a and b, that slope is attained. Okay, essentially, this is Rowe's theorem on its side. Okay, so on the bottom of 288, figure 3, okay, continuous, closed interval, differentiable, open interval, but the two endpoints are not the same height. So there's a certain slope. Mean value theorem says somewhere between a and b, we have that slope. So let's pretend this slope is, I don't know, looks like it's negative. How about it's negative a half? Somewhere the slope is negative a half. That's what they call c, that x value is c. Okay. This figure between a and b, they don't have the same height. So this time it looks like the slope is positive. Let me pretend it's, I don't know, 1/3. So somewhere between a and b, the slope is 1/3. That's what they mean by the c. Here there's c1 and c2. In essence, this is Rowe's theorem slanted. Okay, so if I take the mean value, if you ignore the fact that I'm tilting the book, and you only look at this, I could kind of do this or force yourself to think of this as being quote unquote straight, you would look at this and say, oh yeah, there's Rowe's theorem, slope is 0. Okay, or the next picture, if I can kind of turn the book, right? So that Rowe's theorem applies. In fact, for the proof of the mean value theorem, you actually employ Rowe's theorem. And if you look at this and say, oh yeah, slope is 0, somewhere the slope is 0, here are those points. Okay, so the mean value theorem is basically just Rowe's theorem tilted on its side. If the two endpoints are not of the same height, you have some slope. Somewhere that slope is attained between a and b. Okay. That's the mean value theorem. And back to number 3. Okay, so part A, verify that the function g satisfies the hypothesis of the mean value theorem. All right, so it's drawn continuous on the closed interval, differentiable on the open interval. See, how do you know it's differentiable? You can draw a tangent line anywhere. Okay, difference between this and Rowe's theorem. Rowe's theorem, the two endpoints have the same height. Here, the two endpoints do not have the same height. Therefore, there's a slope associated with them. Okay, that slope turns out to be 3/8. It looks like it says 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. So the slope is 3/8. Okay, estimate the values of c that satisfy the conclusion of the mean value theorem on the interval from 0 to 8. Okay, so what's essentially happening now is you have this slope here. Okay, you're trying to keep that slope. So I'm trying to draw a parallel line, trying to go straight up to there and maybe come down to here also. So the slope is also 3/8. Okay, so up here, it looks like it's approximately 2. Okay, and if I come down to here somewhere, okay, so offhand, I would say it's roughly whatever this is, maybe 7. Okay, so the answer to B, I would say, is 2 and about 7. Part C, estimate the values of C that satisfy the inclusion of the mean value theorem on the interval from 2 to 6. So we're pretending only that we're between 2 and 6. The rest of the graph does not exist. So blot out of your mind the rest of the graph. We're only going from 2 to 6. So the slope now looks like it's going from there to there. So I'm playing the same game here. And if I go this way, it doesn't look like I'm getting that slope anywhere. So maybe just over here somewhere. All right, so my guesstimate is somewhere around here. Offhand, I would say that would be 4. So I would say the answer to part C is 4. Okay, and 4.213. Verify the function satisfies the hypothesis of the mean value theorem on the interval from 1 to 4, then find all numbers C that satisfy the inclusion of the mean value theorem. Okay, so 11 and 13 are like that. I'll do 13. Natural log of x from 1 to 4. Okay, but we know the natural log of x is differentiable. How do I know? I can find a derivative, 1 over x. That's well defined everywhere. That the ln x is defined, which is all positive quantities. So therefore, by extension, it's continuous on closed interval 1 to 4, differentiable, open interval 1 to 4. Okay, so the mean value theorem applies. So I find a slope, f of 4 minus f of 1 divided by 4 minus 1, which is natural log of 4 minus natural log of 1 divided by 4 minus 1, ln of 1 is 0, so ln 4 over 3. The slope of the line joining x equals 1 and x equals 4 is this thing. So the mean value theorem says somewhere between 1 and 4, this is the derivative. Okay, find that C, so-called. So the derivative of ln x is 1 over x, set it equal to ln 4 over 3. Okay, flip both sides, reciprocate both. So x is 3 over ln 4. You can use your calculator, that's about 2.16. So that's my C value. Okay, and that is indeed somewhere between 1 and 4. Okay, problem 15. Find a number C that satisfies the inclusion of the mean value theorem on a given interval. Graph the function, the secant line through the endpoints, and a tangent line. Okay, so f of x equals square root of x from 0 to 4. Okay, the function is continuous on 0, 4, differentiable on the open interval 0 to 4. Okay, here's what the square root function looks like. The derivative is 1 over 2 x to the negative a half, which is 1 over 2 radical x. Okay. What's the slope of the line joining the two endpoints? This is the secant line. So if I'm at 0, 0, I go to 4, comma 2. The slope is 2 minus 0 over 4 minus 0, that's a half. So I set this equal to half. That's easy, x equals 1 or c equals 1. So the point is 1, 1. So the slope joining the points from 0, 0 to 4, 2 is 1/2. Mean value theorem says somewhere between 0 and 4, the slope is a half, and we found that it occurs at 1, 1. Okay, and 17, finally. 17, that f of x is x minus 3 to negative 2. Show that there's no value of c in 1, 4, such that f of 4 minus f of 1 equals f prime of 4. F prime of c 4 minus 1, why does it not contradict the mean value theorem? Okay, so what do they mean by that? Okay, so this is 1 over x minus 3 squared on 1, 4. First, I'll plug in 1. Plug in 1, I get 1/4. Plug in 4, I get 1. So 1 comma 1/4, 4 comma 1. Slope is y2 minus y1 divided by x2 minus x1. 3/4 divided by 3, which is 1/4. But they're saying nowhere between 1 and 4 is a derivative equal to 1/4. We can show that pretty easily. Okay, the derivative of this is negative 2 x minus 3 to the negative third, or negative 2 over x minus 3 cubed. Set it equal to the 1/4. Cross multiply, x minus 3 cubed is negative 8. Take the cube root, x minus 3 is negative 2. X is equal to 1, which is not strictly speaking between 1 and 4. Okay? And why does this not contradict the mean value theorem? Well, the function is not continuous at x equals 3. So it's not continuous everywhere between 1 and 4. I'm not allowed to plug in 3 to the original function, as you see right here. Okay, all right, so that is Rowe's theorem and the mean value theorem.